Good morning.
Good morning.
My name is Mike Goodson, and this is my presentation on motherboard technologies. Here we go. Now, who all knows what a motherboard is? Yeah, figured that. We should, right? So, a motherboard is a complex printed circuit board, PCB, which is the main central part of many electronic systems, particularly computers. They are alternatively known as main board, system board, or logic board, as in Apple computers. But it is a platform that offers electrical connections through which other components of the computer communicate, and also houses the central processing unit, the CPU, generally referred to as the brain of the computer. And motherboards are present in almost every electronic device today, including appliances, mobile phones, clocks, televisions, remote controls, etc. They include a lot of essential components of a computer, such as a microprocessor, storage memory, main memory, and the microprocessor supporting chipset that provides an interface between the CPU and other external components. This vital piece of technology revolutionized the way computer systems were later designed. The earlier versions weren't as efficient and dependable. Today's motherboards contain more or less of the following parts. There are non-volatile memory chips that contain BIOS or firmware of the system, sockets that allow one or multiple microprocessors to be installed. Many computers come to the CPU directly welded to the motherboard. Connectors including PATA and SATA that support input devices. Power connectors that use electricity from a computer power supply to run the expansion cards, memory, CPU, and chipset. There are also expansion card slots, graphic cards supported with 2D and 3D graphic capabilities, USB controllers that can support about 12 USB ports, integrated sound card. A clock generator is a vital component that sets the system clock signal to help sync itself to a variety of components. So before the invention of microprocessors, computers were built into mainframes with components which were connected by a backplane that had countless slots for connecting wires. In old designs, wires were needed to connect card connector pins, but they soon became a thing of the past with the invention of printed circuit boards, or PCBs. The CPU, memory, and other peripherals were all housed on this printed circuit board. But during the late 1980s and 1990s, it was found that an increasing number of peripheral functions on the PCB were more economical, hence single integrated circuits, or ICs, capable of supporting low-speed peripherals like serial ports, mouse, keyboards, etc., were included on a motherboard. By the late 1990s, they began to have a multifaceted platform integrated with audio, video, storage, and networking functions. Higher-end systems for 3D gaming and graphic cards were also included later. But since the motherboard's inception, technology has grown in leaps and bounds to accommodate the needs of the modern-day man with faster, lighter, high-end capabilities. The need to reinvent and advance further has only been made possible through the working geniuses behind each technological introduction. With every passing year, we see more innovations break through the market, with others battling out to top off the best. So here's a chronological order of some of the technologies that have come about in the last few years. In 1967, the first floppy disk was created by IBM. In 1970, the first microprocessor was released by Intel called the 4004. Shortly after, Intel announces the release of the first random access memory, RAM, called the 1103. In 1972, the invention of the compact disk. And then in 1974, the 8080 microprocessor was released by Intel. In 1975, introduction of Apple I, of course the company Apple Computer was founded by Steve Wozniak and Steve Jobs, a device that consisted of a motherboard, a keyboard, and a display. In 1977, the first commercial network, ARPANET, is developed, where Apple II takes the market by storm with the first personal computer that integrates the use of colored graphics. In 1980, Paul Allen and Bill Gates are hired by IBM to create DOS. Microsoft in the same year licenses Unix and starts to develop a PC version called Xenix. In 1987, Elite Computer Systems Company Limited is established in Taiwan and becomes the largest supplier of motherboards in the world, manufacturer in the world. In 1997, Intel Corporation, In 1997, Intel Corporation plans to add to its monopoly a microprocessor by manufacturing motherboards. And then in 2000, ATI Technologies Incorporated announces graphic cards technology, an advancement in computer graphics. And then in 2007, ASUS Tech becomes the world's largest maker of computer motherboards. And in 2011, Intel announces the commercialization of 3D transistors. Also in 2011, the first 4 terabyte hard drive is released by Seagate. And then in 2012, Raspberry Pi, which is a bare bones, low cost credit card sized computer, is released to help teach children to write computer code. In 2012, Intel demonstrates its next unit of computing, a motherboard measuring only 4 by 4 inches, just 10 by 10 centimeters. In 2012, TDK unveils a 2 terabyte hard drive on a single 3.5 inch platter. The first 8 terabyte hard drive was released by Seagate in 2012 also. And motherboards used to be complicated, and blowing one up wasn't that difficult. Components could be plugged in backwards. There were jumpers and dip switches that required a manual and some experimenting to work your way around. There were no software utilities to play with, and no 2 boards appeared to be laid out in the same way. These days they're robust, easy to use, and designs are fairly uniform. Prior to 1987, IBM computers used large motherboards. After that, however, the size of the motherboard was reduced, and boards using the AT, which is advanced technology, form factor was released. The AT form factor is found in older computers, 386 class or earlier. Some of the problems with this form factor mainly arose from the physical size of the board, which is 12 inches wide, often caused the board to overlap the space required for the drive base. Following the AT form factor, the baby AT form factor was introduced. And with the baby AT form factor, the width of the motherboard was decreased from 12 inches to 8.5 inches, limiting problems associated with overlapping into the drive base area. Baby AT became popular and was designed for peripheral devices such as the keyboard, mouse, and video to be contained on circuit boards that were connected by way of expansion slots on the motherboard. The Baby AT was not without problems, however. Computer memory itself advanced, and the Baby AT form factor had memory sockets at the front of the motherboard as processors became larger. The Baby AT form factor did not allow for space to use a combination of processor, heatsink, and fan. The ATX form factor was then designed to overcome these issues. And I have the video.
Hi, this is Gabe Grabning with AMD, and I'm here at our AMD Fusion Developer Summit in our Experience Zone. We've got a lot of great demos here. I'm joined by Ed Holloway, also with AMD, who's got some pretty cool stuff to show us. Ed, what have you got going on here?
Well, these are some of the things you can build with APUs to take advantage of the fact that they're very strong, powerful computers, but they're actually very small and use very little power, so they don't get hot. This is an entertainment computer. It's built with a Llano APU using a mini ITX motherboard, and if you're used to big motherboards, mini ITX is a size that's about this big. Now it's got enough compute power to be useful. So we're running on a 1920 by 1200 screen. It's a lot of pixels to drive. We're playing a Blu-ray video in the background. There's the Blu-ray light going there. We're playing Big Buck Bunny from a drive. That's a 1080p video we're decoding and displaying. We're also running Dirt 3 in the background. But we can do all of that in a very small box. And if you were here, you'd realize this box is very cool if you put your hand on it.
Yeah, that's very cool. So this is for home theater PC. This type of box can do everything that you want to do at 1080p.
And it's not big, and it's not noisy, and it's not hot.
So we're decoding a DVD, watching another video, playing a game all at the same time.
Yeah, and the CPU meter is going somewhere between 40 and 55% or so. So we're not fully taxing this APU at all.
That's amazing. And what makes a difference between the APU now versus home theater PCs of the past?
This whole system is running on 120 watt power supply. The power supply is a little brick up the back. Inside there's just a little regulator board.
So power efficient, and yet has all the performance to do everything you need.
Yes.
Very cool. All right, well, so that's this one. What do you have over here?
Well, if you're used to building home PCs for gaming or your home office, you usually start with a big case and a big CPU and a great big heatsink. This is one of my favorite Cooler Master heatsinks. that I use a lot. But here it is a little differently. That fan is really just for show.
Don't do that at home, kids.
Yeah, what this thing that looks like a fan is doing is it's running a video game. So that's running Dirt 2. And what's running it is, if you look at the back of this, where the other fan should be is a complete APU-based computer on a nano ITX motherboard.
So that's pretty amazing. You got the whole PC right all within this space here.
That's a full PC. It's got Wi-Fi, Bluetooth, all the connections are on the bottom, and the entire fan for that system is this little tiny fan inside there.
Wow. So you're delivering, that's the entire PC right there, and you're playing a DirectX 11 based game. Wow, that's amazing.
This is another prototype we did. This is a complete computer that sits in a little power brick. Plugs into the wall. There's an SD slot, and there's HDMI, Ethernet, and USB ports on the back. So that's a complete computer.
You got the complete computer plus the power supply all in that,
Yeah.
the size of a power supply from other PC, man.
Yeah, so this is mini ITX, this is nano ITX, and this is ridiculously small. It's just inside the power supply.
All right, ridiculously small. All right, well, hey, that's good stuff. It's really some amazing stuff that you can do with home theater PC and the AMD APUs. This is Gabe Ravening. Thanks for tuning in.
Little thing's pretty cool, and how small computers are nowadays. That's pretty cool. To continue with some form factor motherboards. That's the ATX, with the need for a more integrated form factor, which defines standard locations for the keyboard, mouse, I/O, input/output, and video connectors. In the mid-1990s, the ATX form factor was introduced. Since expansion slots were put onto separate riser cards that plug into the motherboard, the overall size of the computer and its case was reduced. Some of the design improvements of the ATX form factor included a single 20-pin connector for the power supply to blow air into the case instead of out for better airflow, and integrated I/O port connectors soldered directly onto the motherboard. The ATX form factor was an overall better design for upgrading. Then we have the micro ATX, which it followed the ATX form factor and offered the same benefits, but improved the overall system design cost through a reduction in the physical size of the motherboard. This was done by reducing the number of input-output slots supported on the board. The micro ATX form factor also provided more I/O space at the rear and reduced emissions from using integrated I/O connectors. Then we have the mini ITX, which was developed by VIA Technologies in 2001. They're commonly used in small form factor computer systems. Originally designed to be able to be passively cooled with a low power consumption architecture, which made them useful for home theater PC systems where fan noise can detract from the cinema experience. The four mounting holes in a mini ITX board line up with four of the holes in ATX specification motherboards, and the locations of the back plate and expansion slot are the same. Many ITX boards can therefore often be used in cases designed for ATX, micro ATX, and other ATX variants if desired. Then we have an LPX, which the LPX form factor is found in low profile cases, desktop model as opposed to a tower or mini tower, with a riser card arrangement for expansion cards where expansion boards run parallel to the motherboard. While this allows for smaller cases, it also limits the number of expansion slots available. Most LPX motherboards have sound and video integrated onto the motherboard. While this can make for a low cost and space-saving product, they are generally difficult to repair due to a lack of space and overall non-standardization. The LPX form factor is not suited to upgrading and offer poor cooling. And we have the NLX, which boards based on the NLX form factor hit the market in the late 1990s. This updated LPX form factor offered support for larger memory modules, tower cases, HDD video support, and reduced cable length. In addition, motherboards are easier to remove. The NLX form factor, unlike LPX, is an actual standard, which means there is more component options for upgrading and repair. Many systems that were formerly designed to fit the LPX form factor are moving over to NLX. The NLX form factor is well suited to mass market retail PCs. And then we have the BTX, or the Balanced Technology Extended form factor. Unlike its predecessor, is not an evolution of a previous form factor, but a total breakaway from the popular and dominating ATX form factor. BTX was developed to take advantage of technologies such as serial ATA, USB 2.0, and PCI Express. One of the more popular features of the BTX form factor is that it uses inline airflow. In the BTX form factor, the memory slots and expansion slots have switched places, allowing the main components, the processor, chipset, and graphics controller, to use the same airflow, which reduces the number of fans needed in the system, thereby reducing noise. Speeding up your system was once a secret craft, but now it is a major feature of what the manufacturers call enthusiast motherboards. And a good thing too, given the way the processors are still sold running at less than full capabilities. Not attempting to unlock some of that extra speed would be a crime, wouldn't it? Enthusiast boards from the main players all come with an array of software and hardware tools for the job. These overclocking abilities have long been the major battleground between the top motherboard players, each producing specialist overclocking or gaming boards, often bristling with other specialist silicon and elaborate cooling arrangements. MSI also has a custom chip dedicated to overclocking through OC Genie, which can operate completely in hardware. This feature auto-detects the overclocking potential of your processor and memory, and you simply push a button on the board and bingo. In about 5 seconds, it has run through the possible timings and voltages available and found the highest stable settings. In theory, of course, one that's great for the overclocking aficionado. And there's a little picture of it, which is pretty cool if it works that good. Just push a little button and bam, it does everything for you. Kind of takes the fun out of it though. Wow, did that one too big. Well, okay, I'm sorry, I can't really talk. But able to supply steady and accurate power levels, components such as these matter when you start stepping outside design parameters. The top boards from all these players can make a good job of overclocking. Chips can be unlocked and you have access to all sorts of arcane voltage and frequency multipliers through the BIOS, custom hardware, and specialist software. Basically, all the decent boards give you enough tools for playing with voltages in one way or another, so that it largely comes down to your experience and the quality of the processor and memory, how much you can bring from your box. The other feature that gets the big shout out is going all green and reducing the power consumption. Let's ignore the obvious irony that this is pulling in the other direction to the other big sell of overclocking for a moment. The way to save power is to turn things off or down. A lot of this technology is built around PWM, pulse width modulation. If you remember your basic electric circuits, then the easy way to reduce current is to add a resistor. And if you want a variable power, then you pop in a rheostat. Trouble is, this wastes power in the form of heat. PWM circuitry basically just switches the power on and off very quickly, effectively reducing overall draw without wasting energy. PWM fans are pretty commonplace now, but the system can be applied to other components. Well, cut off the top again. But the features are about tapping into the abilities of other components, controlling a fan or throttling back an Intel chip, for example. It's about the control of parts not required all the time, rather than the inherent power reduction, which probably tells us something about the difficulty of reducing the motherboard's own power requirements. Decent energy saving, not capable of overclocking, requires hardware support and another custom IC on board. We can expect the power saving capabilities of boards to be pushed further as better control chips are added. There are limits, of course. There's only so much you can turn off. Video. Let's go to the top 10 motherboards today. Just around. Kind of interesting to see all the technology, heat sinks, and colors, and craziness. control, it really just holds it in. That's a lot. It's like a little city now. And thank you very much. That will conclude my presentation. Or does anybody have any questions about motherboards? I probably. Maybe I've answered. All right, thank you.